Hi, my name is Gene Chagas-Vass, and today I'm presenting on humanoid local manipulation of pushed carts utilizing virtual reality teleoperation. This work was performed by myself, Dylan Wallace, and Dr. Paul All. Material handling is present on our day-to-day lives. When we go to the supermarket, we store our groceries on a cart. The action of manipulating and moving the cart simultaneously is what we call loco-manipulation. Upon a deep search in the literature, it becomes clear that material handling of objects is a common occurrence when it comes to search and rescue, disaster response, etc. More often than not, first responders and firefighters utilize carts to facilitate their jobs. It is quite clear that in many instances, high risk jobs may or may not represent a danger to the worker. Therefore, we, the humanoids research, ought to seek a solution where robots are just as good on performing high-risk tasks as their humans counterparts. And by doing that, we can ensure the workers' safety. It has been a long-lasting tug-of-war between autonomy and human-controlled systems. There are advantages and disadvantages within both realms. However, it is irrefutable that in many areas, human expertise and human intuition still provides the most desirable outcome. With that in mind, we propose a method where the expert operator can embody the robot. In other words, he or she can become the robot. By adding human intuition into the equation, we can evaluate the humanoid's ability to not only manipulate objects in place, but also material handle them. Conversely, in previous work, the authors had to constantly recalculate, simulate different carts' dynamics. Now, we seek a system where the human operator decides what is the optimal way to grasp and push a cart. Here one may observe that we're using the DRC-Hubo humanoid as a testing platform and the HTC Vive headset providing the operator with a fully immersive experience. To provide such immersiveness, we've utilized a RealSense camera where via point cloud, the operator can easily manipulate the robot. Note that the top figure on your left depicts how the virtual model conveniently overlaps with the real humanoid's model, allowing the operator to have a semi-real-time manipulation experience. Moreover, the vision is being rendered through Unity, as seen on the system framework diagram below. Such system also showcases how the motion commands are interpreted via ROS, which directly interfaces with POTO. POTO is the DRC-Hubo humanoid real-time thread. Now let us take a look of some of our experimental runs, as well as some of our results. I'll let my colleague Dylan Wallace take from here.
Hello, I'm Dylan Wallace. In this first clip, we see the operator manipulating a cart that has been studied in previous work as a validation method for the new virtual reality approach. The operator uses the virtual teleoperation framework to manipulate the robot's end effectors in order to grab the handles of the cart. The operator does not have direct access to what the robot is seeing, as would be present in a remote operation approach, so they must use visual feedback provided via the virtual reality interface. The visual feedback seen by the operator can be seen in the video of the lower right corner. The operator is able to see both a model of the current joint state of the robot and a real-time stream of color and depth data from the actual robot. The operator has the ability to change the direction of this visual feedback via the orientation of their virtual reality headset, allowing a much wider field of view of the robot's environment to be obtained. The operator can change the walking state of the robot via the interface menu seen in the lower right corner's video. The operator can then use the virtual slider circled in red to steer the cart in a desired direction. We can see from the first attempt some promising results at pushing carts that have been previously encountered by the robot, but this time using the new virtual reality approach. This next clip shows a longer validation effort for 50 steps and focuses on the steering capabilities of this local manipulation interface. The operator has already grasped the handles of the cart in this experiment and will initialize the walking sequence. The operator is tasked with steering the cart in order to center on the white line with slight curves in it. The operator uses the provided visual feedback from the robot to attempt to steer the cart in the right direction with the virtual slider. We can see that the robot struggles at first to maintain the line, but it is adjusted as the operator compensates via the steering slider. Both the robot direction and the direction of the cart are adjusted via this slider. This task is harder for humans to perform, as these types of carts are hard to steer without a loaded weight on the cart. This next clip demonstrates the strengths of the new virtual reality approach in being able to loco-manipulate carts which the robot or the operator have never encountered before. This clip is the very first time a cart of this style has been attempted to be pushed by the robot, including previous work. We can see that it takes some time for the operator to determine the best method to grasp the utility shelving cart, as it is the first time they are encountering it, and they do not have the prior knowledge of how to best push this cart or the dynamics of the cart. One useful feature that the virtual teleoperation framework provides is the ability for the operator to detach themselves from the body of the robot in order to get a better view of how the robot is manipulating the cart. This is possible due to the nature of the color and depth data provided as visual feedback. The new feature of moving the orientation of the visual feedback further enhances this feature. We can see the operator bending down in order to better visualize the depth data of the robot and to ensure that they get the best grasp on the cart. As a safety mechanism, there is a check on the arm controller to determine if the grasp position of the cart can be executed in the walking state. This is done via validation of the whole body inverse kinematics and will prevent the robot from transitioning to the walking state if the joint configuration is invalid. We will see in this video clip that the grasp position from the operator is indeed valid, and the robot will walk as instructed. However, this experiment involves no steering component, and thus the direction of the cart and the robot will drift depending on the walking dynamics. This last clip will demonstrate an attempt at the shelving cart using a second operator, as well as the MATLAB validation used in this work. In previous work, the DRC-Hubo was required to have pre-programmed grasping positions tuned and validated manually for each different cart it tried to loco-manipulate. However, with our new approach, it is great to see that the robot is able to loco-manipulate on carts that it has never previously encountered, and could open the doors to more complex cart pushing endeavors for the robot. We can see in this clip that the second operator is able to also find an ideal grasping position for the robot, and is able to loco-manipulate the shelving cart via the robot with ease. The MATLAB validation in the upper left corner represents the robot's joint states during this experiment, with lower body IK generated via MATLAB simulation based on the upper body data obtained during experiments. Lastly, we will see some quantitative results of the robot's walking performance with this new approach. This plot compares the measured XCMP of the robot during the experiment with both the hand cart shown in the first two video clips and the shelving utility cart seen in the last two clips. We can see that both the XCMP for the two carts remains within the support polygon of the robot, and they both tend to follow the reference XCMP throughout the walking process. The same comparison is also shown on a plot for the YZMP of the robot. We can see again that the YZMP for both carts tends to generally follow the reference YZMP of the robot. The spikes seen in measured YZMP for both the hand cart in green and the shelving cart in blue represent the attempt from the operator to steer the cart via the virtual interface. However, despite the instability that this may cause, the robot is able to compensate and properly steer toward a desired direction. The new approach presented has been shown to be broadly applicable to all four-wheeled carts, and allows for the robot and the operator to seamlessly interact with any cart. The authors thank efforts of the members of DASL listed here at the end of this video, and we thank you for taking the time to watch this video of our approach.